Okay, we should get started. It's about time. Okay. All right, so hello. I think this is week 12, right? Yeah. So the reading now is Parable 29. I think this is kind of a shorter chapter. It's on type safety and soundness, which sometimes those mean the same thing. Soundness of the type system means that the language is type safe. And so yeah, we're going to be talking a bit about this kind of thing today. And of course, so they use I used the word safe a few lectures ago to mean something a little bit different from what they're saying. They're just using it here as a synonym for type safety. And so we'll get to what that means. So, but they're saying that, a language is safe if it's type safe. Where I said something like, a given program is like safe if it doesn't throw an error or something, but it's not quite the same way that they're using the term safe here. Well, that's okay. All right, and yeah, we'll have a quiz this weekend, Friday, just like normal. Yeah, okay. So I guess I have a plan for today, for something to do. To kind of pick back up on what we started last time, because what we were looking at on Friday was this idea of small step operational semantics, where, before we were using evaluation semantics or big step semantics. So let's remind ourselves what that was. Here's Scheme 1 core big step. So this was a document that kind of, it specifies the semantics of the language using this big step relation that tells you when an expression evaluates to a certain value, all in one big step. Okay? And then we started looking at an alternative formulation of this, where instead of stepping all the way to a value in one big step, the relation we give just tells you how to step from one expression to another, performing a single step of computation. All right, so I want to revisit that, and the way that we'll do it, and in case you're curious, I'm not going to look at it now, but I added a small step semantics for Scheme 1 core, so if you're interested to see how it differs, this should be equivalent to the big step semantics, but it's presented in a small step way. Okay, so now instead of a big fat arrow pointing down, it's this long arrow pointing to the right. And you've got rules that look like this. If you recall, this is called a congruence rule, where you're saying, well, if the sub-expression can take a step, then you can just allow it to take a step, and so this is the congruence rule for Boolean negation. Okay, and then once the sub-expression is actually a value there, a Boolean value, then you can actually perform the computation. So here's the computation rule for Boolean negation. Okay, so for all the different syntactic forms, you've got some congruence rules and usually one computation rule, but sometimes there's more than one computation rule. Like for conditionals, let's look at this one. What do you do first? Well, you evaluate the guard condition as long as it can take a step. You just keep doing that, and then once it's either true or false, then you can apply one of the computation rules to say, either take the left or the right. Okay, so what I want to do now, this is what we had started last time, but I want to do something kind of new here. That we're just going to use a little programming language that's kind of as simple as possible, but enough to illustrate the technique for doing this. Okay, so I'm going to introduce a little programming language that will have First, I'll give the expressions. Okay, so here are the different kinds of expressions. Okay, a number is an expression. The Boolean true is an expression. The Boolean false is an expression. We'll have addition, which I'll write like this. Okay, it's familiar syntax for us. We'll have equality comparison of expressions. And then we'll have conditionals. If E, then E, else E. Okay, so this is it. These are our expressions. We've got numbers, booleans, addition, equality, checking, comparison, and conditionals. Okay? And then I'm going to single out, or I'm going to kind of carve out a subset of these that will be the values. I'll say, well, some of these are the values of the language. So I'll write it like this. I'll say, well, the values are numbers. I should do it the same way. The Boolean true and the Boolean false. Okay, so that's a subset of the language that we say are the values. So then these ones are not values. All right? So now what I want to do first is to give a small step operational semantics for this language. So we're gonna write out, how do programs in this language execute in a small step style. Okay? And so, well, right away, the values, they don't actually take a step. There's nothing that they can do. Whenever you've got a value, it doesn't take any step of computation. It's done computing, There's nothing left for it to do. So we're not going to have any rules for the values, and we'll just have rules for these three syntactic forms here. Okay? And just like before, for each one, we'll have some congruence rules, and then 1 or 2 computation rules, depending on what they are. So let's go ahead and write them out. So suppose you've got an expression that looks like this, plus E1, E2. We want to know what it steps to. Well, this is going to be our first congruence rule. So we'll let this one step to E1 prime, E2, whenever E1 steps to E1 prime. Okay? I'll call this E. We'll call this rule E plus 1. Okay? And then we'll have the second congruence rule that will apply whenever E1 is actually a number. So then plus N1 E2 can step to plus N1 E2 prime whenever E2 steps to E2 prime. I'll call this rule E plus 2. Okay, and then we can have our computation rule that says plus N1 and 2, whenever they're both numbers, can step to N1 plus N2. Okay, where you actually perform the computation there. And we'll have nothing above the line there because there's nothing else required. And I'll just call this E plus. Okay? And so here's the semantics of our addition expressions, okay, in small step style. Pretty straightforward. It tells you the order of evaluation, right, that you have to do the left one first because, well, suppose that you've got some arbitrary expression E1 and E2 here, and you want to use these rules to evaluate the second one first. You're not necessarily, yeah, you can't do that. The only time that you're allowed to evaluate E2 is when the first one is already a value, right? You can only do that when this is a number already. Then you can start to evaluate the second sub-expression. And then once it's a value, you can then finally apply the computation rule. Okay? So that's pretty straightforward. And it's going to be very similar for equality, where, well, we're just going to have the congruence rules, say evaluate the left first, and then you can start to evaluate the right, and then there will be a computation rule. And it really is pretty much the exact same thing. So I'll write them quickly. So if we have equals E1, E2, that can step to equals E1 prime E2. Whenever E1 steps to E1 prime. Okay, we have equals n1. We're going to say it has to be a number, where you can only compare numbers. Okay, then this will step 2 equals n1 e2 prime. Whenever e2 steps to e2 prime. Okay, and we'll give names to these e1, e2, and then we can have the computation rule. When they're both numbers, they will just step to, maybe I'll write double equals to make it really obvious what we're doing there. Oh, yeah. Call that e-eq. There's the computation rule. All right, so we've done the congruence rules and the computation rules for both plus and equality. And now we have to deal with the if then else. And again, this is fairly routine. There's not much going on. We're just going to need congruence rules for all the sub-expressions. And then actually, we only need a congruence rule for one. I forgot. It's an easy mistake to make. So let's write it out. So suppose you've got if E1, then E2, else E3, and you want this to step to E1 prime, then E2, else E3. Okay, so here's the congruence rule, where you're stepping the first expression. Okay, but then we don't need to have congruence rules for the others, because once E1 steps to a value, well, then you can go ahead and perform the computation to take one of the branches, okay, and then start evaluating that branch with subsequent steps. So let's go ahead and do that. If true, then E2 else E3 can step to E2. That's one computation rule. And if false, then E2 else E3 steps to E3. We can give these names like E if 1, E if true, and E if false. Okay. So, and here we go. That's it. Now we have all the rules that we need to specify the operational semantics of this language in small step style. All right. And so, if you notice, for example, like what if you've got an if expression and you're evaluating it by taking steps, and you're saying, okay, well, evaluate E1 until it's a value. And then what if it's a number, actually, when you get to that point? Well, then you'll be stuck, because now none of the rules apply. This first one won't apply anymore, because a number can't take a step. So you wouldn't be able to use the congruence rule anymore. But then you also can't apply either of these, because a number doesn't match. Okay, so you'd be stuck. So if you recall, that's the word for that. Whenever you can no longer take any step, and you're not already at a value, then you're stuck. And that would be the situation where you've got an if expression that can't take a step because there's a number in this spot. Okay, so that would be a stuck expression, and that's how we model runtime errors in small step semantics. Yeah? Oh, sorry, it's just E2. Okay. Right. So these are the small step semantics. Okay, and so you could translate this into code, and let's see if I want to do that or not. Okay, but there's a relatively straightforward way to translate this stuff into code. Okay, so I guess we can do that really quickly. Go ahead and just kind of borrow here. I'll use the smallstep.r file again, where we'll have a data type first for the abstract syntax for this language. okay, where we'll have numbers and we'll also have true and false. So I'll say E true, E false. We have E plus. Okay, I can call these E1 and E2. What else do we have? We have equality, E eq. Like that, and then if then else, E ite, E1. Okay, so there we've translated the syntax into Pirate. Should be okay. And then, well, some of them are considered to be values, so I could go ahead and write a predicate for that to say, well, an expression is a value whenever, let's see, I think you can do like, I think Pirate automatically generates some of these for us, so perhaps we can do if it's this or true. We'll give it a shot, see if it works. Okay, see if it works. Identifier E is not. Okay, that'll work. Okay, so those are the values. And now we want to translate the step relation into a function. Okay, and we can do this because, like I mentioned before, this step relation is deterministic. That at any given point in time, only one rule could apply. Right? There's never a situation where you're in the course of evaluating and there's more than one choice that you could take. There's never any ambiguity. There's only one possible choice to take. So another word for that, for a deterministic relation, where the output is it's determined uniquely from the input. Let's just say it's a function. Right? It's a functional relation. And so that's why we can translate it to a function that you can just know which rule to apply, and there's only one choice. Okay, so let's go ahead and try that. We'll have to do cases. X, E. If it's a number, we're not going to do anything. If it's true, not going to do anything. If it's false, not going to do anything. Okay, so remember, whenever none of the rules apply, then we'll just return the original expression unchanged. That's what we do. And so since there are no rules for the values, then that's what we do. Okay, but then what about in E plus? Okay, now we've got an E plus. And, well, there are three rules that you could possibly apply for E plus. So we need to figure out which one. And so, well, what do you need to know? Well, we need to know whether E1 is a value or not. Or really, if it's a number or not. Okay. So first, I'll check that. If is enum E1, that'll tell me if E1 is a number or not. Okay. If it is, then we'll do something. Otherwise, we won't. Okay. So if E1 is a number, that means we're not going to be able to apply the first rule. Okay. But we could do either one of these possibly. So now to choose between these two, well, we need to know if E2 is a number. So let's check that here. If is enum E2. If it is, we'll do something. Else do something else. Okay? So now if both E1 and E2 are numbers, then there we know that this rule should apply. So I guess it's kind of annoying. I have to pull out the number. So perhaps I should have used cases instead. Let's do that. X, E2. Get a syntax right. Okay, so here's where you can do that. Else something else. Let's clean this up. Okay, so now here we're in the case where both E1 and E2 are numbers, and we can apply the computation rule. The computation rule just says, well, to take the two numbers and add them together to produce a new number. So that's what we'll do. I'll put that there. Okay? But then there are the other cases to consider. So here is where E1 is a number, but E2 is not. So which rule applies in that case? Well, that's this one, E plus 2. The congruence rule, where E1 is a number, but E2 is not. So we just need to let E2 take a step, or try to at least. So we'll step E2, and then reconstruct the original term like that, because it's a congruence rule. You're allowing one of the sub-expressions to take a step, and leaving the rest unchanged. Okay?
Does rule 1 say that neither E1 nor E2 are numbers?
Right. Yeah, and it says that somewhat indirectly by just saying, well, who knows what they are? E2 could be a number, actually. We don't know about E2 yet. All we know is that E1 can take a step, and a number can't take a step. So E1 cannot be a number there. But E2 could be a number. You never know. So perhaps when you're evaluating an expression like this, maybe it's some complicated expression for E1, but then E2 is just a number. Well, your only choice is to first evaluate E1 until it is a number, and then you would skip this rule entirely because, well, if E2 is already a number, then this would never apply, and you would just immediately do the computation. But still, this enforces the left to right evaluation. Okay. So this last case is where E1 is not a number, and so we actually don't really care what E1 is there, as I just said. In either case, no matter what, we're just going to apply the first rule to let E1 take a step. So, right, E1 can take a step, and nothing else changes. Okay? So here we go. We've translated the step rules for these plus expressions into a function, a step function. Now, of course, we can do the same thing for equality, E_eq of E1, E2, and they're really similar actually. It has kind of the same congruence rules where you do the E1 first and then E2, and then there's the computation rule where, well, instead of adding the two numbers, you're just producing a Boolean that's true if and only if the two numbers are equal. So all this code will be pretty much the exact same, except this will now be an E. All right, I have to say if n1 equals n2, then E true, else E false. Okay, because I chose to use separate constructors for true and false. So we'll do it like that. Okay, so that one's pretty easy. And then the only thing left is EITE. Oops. Okay, so now we've got one of these conditional expressions, and we need to know which one of these rules do we apply. And well, first, what we need to know is E1 a value or not? Is it a Boolean? I suppose there is something kind of. One thing I should mention here is that this does work out. Like suppose that we were in the plus case and E1 was a Boolean value, right? So then we wouldn't hit this case. It's not a number. We would hit this one. And so we're kind of like trying to apply the first rule. So, maybe it would be better to not do that. But if you look at what happens whenever you try to do that, well, step E1, if E1 was a Oh, there's a syntax error there. If E1 was a Boolean and you try to step it, then it's not going to change anything. So this whole expression will actually still be equal to the original one unchanged. So we don't really have to worry about that. But it might be better to explicitly check the Boolean cases as well to make it more obvious what happens. Okay. And so, we'll do a similar thing for conditionals. All right, let's just check if E1 is a Boolean. Okay. So we'll do cases on E1, and if it's true, then we can do something. If it's false, we can do something. Otherwise, it's not a Boolean value yet, and so we'll apply the congruence rule. Okay, so let's go ahead and do the congruence rule. That's where you step E1 and leave the rest unchanged. Okay, and the computation rules were actually pretty easy, right? Whenever it's true, then you'll just step to the left expression E2, and whenever the Boolean is false, you step to E3. So there we go, just like that. Okay. Now, I've written a bunch of code without running the type checker, so something is probably wrong. Cases and, else and.
That same syntax error with the parentheses.
Okay. Okay. So there we go.
Also, does under EE, do those E plus constructors need to change?
Oh yeah. Good catch. Eek. Eek. That should be okay. Right. So I suppose that this probably works. Okay. So we've just translated the step relation into code, and this step relation is like the single step relation, right? It's this one that's like E steps to E prime, a single step. Okay, and this is the relation that we've defined giving these rules. But once you have a single step relation, then you can use that to define another one that I'll write like this, with a star. This is called step star or star step. Okay, and it's technically what it is the reflexive transitive closure of the step relation. So what this means is to take the step relation and also make it reflexive and also make it transitive, to just kind of do the minimal thing necessary to extend this relation so that it's also reflexive and transitive. So what do those things mean? Well, reflexive just means that I need to add a new page. So what does it mean to be reflexive? Where in the world? Here we go. Okay, so our star step is reflexive. That means, for any expression, E star steps to itself. That corresponds to taking 0 steps. Okay, so you can take 0 steps as well. I mean, it means 0 or more. That's the way to look at it, right? And transitive just means that for all E1, or I suppose E prime and E double prime, if E star steps to E prime and E prime star steps to E double prime, then you know that E star steps to E double prime. Okay? So really what we're doing here, this is just taking our step relation and saying, well, E E star steps to E prime if it can step to E prime in 0 or more steps. Okay? And so that's pretty much what we implemented last time using this eval function. But I suppose this time I should call it something else. I'll call it star step. Okay? So it takes an expression and we'll evaluate it to another expression by implementing star step, to just say, essentially just apply the step function as many times as you can until it doesn't change anymore. Okay? And so we do that. We say, well, let E take a step to give us some E2. And then if E2 is equal to E, then we're done. That means that the step function didn't change anything. So none of the rules applied. We can't make any progress. Else we will continue. Okay, else E2 actually was different from E. Some computation really happened, and so let's keep trying to go further. Star step E2. Okay. Okay, this ended up taking a lot of time, of course. All right. So there we go. And so now this star step relation is the one that really ends up corresponding to the big step evaluation relation that we had before. Okay, so I haven't given a big step semantics for this language, but it would be pretty easy to do in such a way that you could then have the following equivalence between them, where you could say, well, you know, for any expression in the language and any value, right, which is an expression that we consider to be a value, then you know, E star steps to the value V if and only if E big steps to V according to the big step relation. So I'm going to skip doing this in the interest of time. You know, I'm not going to write down the big step relation rules, but we could pretty easily define one, and then it would be kind of interesting to try to prove this. But we're not going to do that. But this is the idea: is that these should probably be equivalent, right? That if you can star step to a value under the small step semantics, then we would expect that to be the same value that the big step semantics gives us. Okay, so that would be the equivalence of the two formulations. But we're not going to do that. And what we're going to do instead is to add a type system. Okay, because as we've noted, there are plenty of ways for this language to go wrong. There are plenty of ways for it to get stuck. Okay, like if you try to add a Boolean, or you try to add two Booleans together, or a Boolean and a number, then you're going to end up getting stuck because this computation rule only applies whenever they're numbers, right? And similarly for equality, we've defined it in the same way, where, well, you can only actually perform the computation when these are numbers. So if you get here and one of these is a Boolean, then you're stuck, okay? And then for conditionals, if you end up with a number in this spot, then you'll be stuck there as well. Okay, so the way that we've defined the language so far, there are plenty of ways for it to go wrong, plenty of ways for programs that are syntactically well-formed to get stuck when you try to run them. Okay, so that's why we're going to add a type system. And we've got enough time, I think, to go ahead and define the type system. All right? Okay, so to do that, I suppose I'll go up here. Well, guess we can start it here. The first thing we did.
The difference between E prime and E star?
Okay. Well, there is no E star. There's a star step, which is like the arrow star. So I use E prime to mean like, you know, just a different E. So, like for example, here we're saying that if E star steps to E prime and E prime star steps to E double prime, then that implies that E star steps to E double prime. Okay, which if you want to think about this in like regular English, it just saying that if E can step to E prime in 0 or more steps, and E prime can step to E double prime in 0 or more steps, well then you know that E can step to E double prime in 0 or more steps. Okay? So it's a transitive relation. Whereas the original step relation was not transitive, the way that we defined it. And so that's why this star thing is called the reflexive transitive closure of the original step relation. It's taking the original one and just extending it so that it is also reflexive and transitive. Okay, and intuitively it just means, 0 or more. It's sort of like regular expressions when you put the little star there, the Kleene star. It's like it means 0 or more, to match 0 or more times. Okay. Okay. So write the type system. So the first thing to do is to say, what are the types? What are the types in this language? And well, we've chosen our language to be pretty simple, so we're only going to have 2 types. Okay, we've got numbers and we've got booleans, and that's it. So these will be our types. Say T. Our language of types will be num or bool. Okay, those are the types. And then once we've decided on what our types are, we can go ahead and write down the typing relation that is fairly similar to the operational semantics, but we're defining the typing relation now instead of the operational semantics. Okay? So I'll write down a few of these rules to start. Okay? So this tells us, when does a given expression have a given type? And so any number will have type num. And there's nothing above the line because you could always show this no matter what. Okay, so this is one of the axioms of the type system, that number values have type num, always. Okay, and we'll do the same for true and false, that the true value has type bool, unconditionally. Any false value has type bool, unconditionally. Okay, and I suppose we should give these names like T num, T true, T false. Okay, so the values are very easy to type. And now we just need to handle these 3 things: addition, equality, and conditionals. So let's come up with some typing rules for them. First we'll do addition. So when you've got plus E1, E2, what type can this have? It will always have type num. Okay, but under the following conditions, that E1 has type num and E2 has type num. Okay, so I'll call this one T plus. Okay, so well, this is the only one you need for T plus. This is the only typing rule you need. You say that, well, a plus expression has type num whenever both of its sub-expressions have type num. Okay, pretty straightforward. Okay, how about equality? If E1 or equals E1, E2, what type will that have? Oh, well, that'll be a bool, because it produces a boolean when you evaluate it. Okay, under the condition that E1 has type num and E2 has type num. Okay, so there's our typing rule for equality. That an equality expression has type bool whenever both of its sub-expressions have type num. Okay, and the only thing remaining is the conditional expression. If E1, then E2, else E3 has type something, I'll call T, whenever E1 has type bool. Okay, the guard condition has type bool, and then E2 has type T, and E3 has type T. So we don't actually care what T is. It could be num or it could be bool. All that we care about is that it's the same for both branches, that E2 and E3 have the same type, whatever it is. And that E1 has type bool. Okay. So this will be T if. All right. And that's it. That's all we need. This is the entirety of the typing relation. It's fully defined here. And it is important to note, though, that it's an inductive relation. This definition here is inductive, which means that it means that these are the only rules. You know, so these are the rules for determining whenever an expression has a type, and they're the only rules. There are no others. So that's an important thing. So that whenever you've got, well, so if you know an expression is well typed, you know that it must have been using these rules and not anything else. Okay. So we'll see probably next time why that's important. Okay. So that's the type system. And now that we've defined everything, I mean, this language here is now, it's kind of fully defined. We've given the syntax. We've given the operational semantics. Okay. And we've also given the static semantics of the type system. Okay. And we've defined them in such a way that hopefully we can prove some nice properties about the language. Okay? And so I'll start off by writing down some of these. And then I think next time, because we don't have time today, of course, we can look at actually trying to prove them. Okay? But let's just state what they might be. Okay? Because essentially what we want to prove here is a type safety theorem, which says basically that if an expression is well typed, if it has a type according to these rules, then when you run it, it won't get stuck. It'll run all the way to a value and never get stuck. And that would be, if that's true, then we could say that the language is type safe. Okay, and so I've tried to design the type system such that that is the case, but it's not totally obvious that it's true. Okay, and so we want to be able to prove that it is. And there's a standard technique for doing that by breaking it up into two pieces. That to prove type safety, we're actually going to prove two separate properties that together imply the language is safe, type safe. Okay? And so the first one is called, where are we at? Progress. Okay? So the first thing that we're going to try to prove next time is a progress theorem that says the following. It'll say this. It'll say, well, for all expressions and types, so for all E and T, where E is an expression and T is a type, then E has type T implies one of two things. Either E is a value, or there exists an E prime such that E steps to E prime. Okay. This is the progress property. What it says is that if you've got an expression and a type, then if the expression has that type, okay, if it's what basically you're saying, if the expression is well typed, then either it's a value or it can take a step. This is the progress property. Okay? That well-typed expressions can make progress, or they're already a value and you don't need to make progress. Okay, so we're going to try to prove something like this. And then the second property is called preservation. Okay. And let's see, how do we write this one? Where's my thing? There we go. It'll be like, for all expressions E, and E prime and T, then let's see, if E has type T and E steps to E prime, then you can conclude E prime has type T. Okay? This is the preservation property. This is stating essentially that well-typed expressions, whenever they take a step, the result is also well-typed. It has the same type. So this is saying that, this is essentially saying that the step relation preserves types. That whenever you step from an expression of type T, you result in an expression of type T, always. Okay? That's the preservation property. And so it turns out, if you can prove both of these separately, then this implies that the language is type safe. Because basically you can use them together. So suppose you've got some expression that you want to run, and you know that it's well typed. Well then, you know by the progress property that it can take a step. Right? Or if you're at a value, you're done. So you'll be having them too. But you know by progress that your expression can take a step. And then you know by preservation that whenever you do take a step, the resulting expression is still well typed. And so then, by progress, that can also take a step, and by preservation, the result from that will still be well typed. And so together, they kind of just, they'll take you all the way to a value, no matter what. Okay? You always know you can make progress, and whenever you do make progress, well typedness is preserved, which guarantees further progress, and so on. Okay? So that's the slogan here is a very famous slogan, which is just type safety, or this is roughly what it is, equals progress plus preservation. Okay? That's it. And you kind of need to have a small step semantics for your language in order to state this properly. I suppose for this language in particular, we could have done this. We could have come up with a similar thing with using big step semantics, but you can't always do that whenever the language is more complicated. Especially when the language has infinite loops, then there really is a difference between the small step and big step semantics. Okay. Well, all right, so we're about out of time. And so this is what I want to do next time, is that we're going to look at how to actually prove these properties for this little language here. Okay? And we could, in principle, try to prove them for scheme 1, although we would have to make some modifications, because I think if we tried, we would actually we would run into some trouble where we wouldn't be able to prove progress probably for scheme 1 core without removing something, but that could be interesting to look at. All right, so let's see if we have a quiz today, and we'll be done. Okay. Let's see. Wow. Okay. See you Wednesday.